So generally the second unit covered in any calculus class is all about differentiation or finding the derivative. But rather than throwing these terms that you probably haven't heard of before, it's probably best to understand what the concept is behind this differentiation or this derivative. And the concept behind it is actually this slope of a point. And I really want you to pause and think about this premise here, the slope of a point. So you have a point right here, and it looks like this red line is grazing it, and then there is a slope to this line. There's a rise over run, a change in y over change in x for that line that's crossing through with that red line. But the interesting thing about this is, if you remember the slope formula, it's change in y over change in x. But that change in y is actually y1 minus y2, and then you're dividing it by the change in x, which is actually just x1 minus x2. And this is equal to the slope. But this is the slope of 2 points. That's in essence what that 1 and that 2 represent. Okay, so right here, that 1 and that 2 and that 1 and that 2, that's 2 separate points. That's 2 separate x comma y coordinates on a graph that you're finding the slope of. This time, we're figuring out the slope of 1 point. So in essence, you can kind of think of it as like y1 minus y1 over x1 minus x1 is equal to the slope of a point, or the derivative. But the problem with this is it's going to equate to a 0 over 0. And this ties directly back into that first unit that we did, where we were solving certain limit problems that resulted in a 0 over 0 indeterminate form. And if you remember, anytime there was a 0 over 0, unless there's an absolute value in the expression, anything that gets a 0 over 0 will have an answer if you use limits. And this is the key to figuring out the slope of a point, is limits. So it all goes back around to that first unit. Limits, you can get infinitesimally closer to some value without ever actually reaching it. So we don't actually have to do the same value minus the same value for the y and the x here to get a 0 over 0. What we can do instead is we can just change this value right here to be getting infinitesimally closer to this value here. And that's in essence what the derivative is. Instead of using 2 points, or instead of using 1 point to find the slope of a point, we're using 2 points, but the points are getting infinitesimally closer together. The same thing can be said about this x1. This is going to get infinitesimally closer to this x1. So it is a separate point, it's just getting infinitesimally closer to it. We're going to go more into a deep dive in this video. This is just kind of an intro to that idea. So just trying to spark your brain a little bit, preload it a little bit with understanding before we get into the to more specifics. So that's just an intro to the to that concept of derivative. One way I like to think of it as well is the old school way of finding slope, with 2 points. That's the average rate of change. Okay, AROC, average rate of change. You've probably heard that before. Where the derivative is the instantaneous rate of change. So you're going to hear me say that later. It's instantaneous rate of change. Rather, it's the change at an instance in time. Okay. One way of thinking about it is, if you were driving in, down a road, and you went here. Let me draw this out for you. But let's say you started here at point A, and you went to point B. Okay, and the distance between these is 50 miles, and it took you 1 hour to go those 50 miles from point A to point B. Okay, on average, you went 50 miles an hour. Okay, that would be your average rate of change. I'm just going to write ROC, average rate of change. Okay, now as you were driving from point A to point B, there might have been certain instances where you were maybe going, 75 miles per hour. Okay, another one, you might have just been going 0 miles per hour because you stopped. The essence is you probably did not go 50 miles an hour the entire time. Sometimes you were going faster, sometimes you were going slower. Okay, these instantaneous rates of change, so this right here, the instantaneous rate of change, I'm going to write IROC, it would be the derivative. Okay, so if a police officer, shot their radar gun at your car, that's a certain instance in time how fast your car is going in that instance. That's derivative. The old school way, that's just finding the slope, the stuff that you've seen before in algebra, that's the average rate of change. That's the 50 miles in 1 hour. You can just take the average of that. Where instantaneous, it's what's going on at certain instances in time. So 75 miles an hour, the 0 miles per hour could also be an instantaneous rate of change. Anywhere in there where it's just an instance in time. And what's great about limits is they allow you to define what an instant is. Okay, because how can you change in an instant? If you were watching, say you were driving a car and someone was recording you, you can't pause it and go, how fast was I going in this instant when you're pausing it? If you're pausing it, you're not changing at all. That would be 0 over 0. But what you could do is look at the frame that's directly before that video of you driving and figure out how fast were you going in that frame, compare it to how fast you were going in the other frame, and then basically do an instantaneous rate of change based on that one. Okay. And again, this is just a brief intro. We're going to go way more into a deep dive. So this is confusing, just me explaining it right now. Just hang tight, watch the rest of the video. It should make more sense. But that's in essence kind of how I wanted to preload your brain with the slope of a point. Okay, so Unit 2, it's called differentiation. Okay, differentiation is the process of finding the derivative. So when you see this word differentiation, it just means the process of finding the derivative. A derivative is also a new term, probably. So derivative, again, just means the slope of a point. So if you're finding the derivative, you're finding the slope of a point. Okay, instantaneous rate of change is another way of saying it. All right, onward we go. All right, a little bit of history on calculus right here. The calculus creator is Isaac Newton. It's been said that Newton was trying to figure out at one instance, if an apple is falling off a tree, how fast is it going in a specific instance? Okay, and he was trying to relate that to math. Like, could math actually figure out that instantaneous rate of change? Some people say that's a myth, though, with the apple falling on his head to give him the idea of gravity and calculus and that sort of thing. But it doesn't really matter. It's just kind of a little side story with Newton. A lot of people say that he came up with it first. But this other guy, Leibniz, he also came up with it independently, supposedly, a few years later. But it is really important to understand that anyone that created anything, really, there's usually tons and tons of people working on that same project. I know we like to, idolize certain people, like, oh, this is the person that did it, they invented it, like they were just like some in isolation. But Newton even had a famous quote where, if he created anything, it was by standing on the shoulders of giants. So by standing on the shoulders of other people's studies, he was able to study other things and figure out other things as well. So I don't put a lot of credence into who creates something. It's not that serious. But a lot of times in history books, you'll see that it's these two guys that come up. And this relates to a little comic, XKCD, made. I don't know if you've ever seen this. It's a webcomic, XKCD. But he makes basically like nerd comics, comic strips that kind of, I think are kind of funny. But it says right here, Newton, I've invented calculus in 1666. Leibniz, I've invented calculus, 1674. And then Newton, so it goes back to the Newton character, you can tell because the hair is matching here. And it says, really, it sounds a bit derivative. Okay. He puts his sunglasses on. That's a nod to a TV show that a lot of people probably haven't watched, but it's not really that important. But the main thing is derivative also means, kind of a copy off of something else. So he's like using the fact that like derivative in calculus also means the slope of a point, but he's saying derivative is like kind of a copy. So yeah, anytime someone says like an art or like music or something is derivative of something else, it usually means it's like kind of copied off of that something else. So that's why I kind of think it's kind of funny. It's that double usage of derivative. Now, it is important to understand that even if Leibniz didn't invent calculus, some of his greatest additions to calculus is just using his notation, which is still important in its own right. So yes, the ideas behind calculus are super important, but a lot of the notation we use, pretty much all of it, it comes from Leibniz. Okay, and if you're ever bored, I highly recommend looking up Isaac Newton's notation, just so you can kind of see the difference between the two and how we use Leibniz's notation mostly nowadays. But anyway, onward we go. This next slide, it shows right here, essential questions. So these are all the questions that you should be able to answer by the end of this unit. Okay, how is the slope of a tangent line calculated? Okay, slope of a tangent line is the same thing as saying slope of a point, because a tangent line is based off of one point. So this first one is just how is the derivative calculated, in a way, if you want to think of it that way. So we're going to figure out how do we calculate these derivatives. The next thing is how is differentiability defined? Okay, differentiability is the ability to be differentiated. It's the ability to have a derivative. So how is that defined? We're going to talk about that. How can a derivative be estimated at a point? Okay, so we're going to estimate derivatives actually just using slope for that one. So estimating derivatives at a point. 4, how are derivative how are derivatives found using differentiation rules? So there's going to be these things called derivative rules or differentiation rules that we're going to use to, procedurally find derivatives of specific, functions. 5, how are derivatives found using basic differentiation rules? There's basic differentiation rules that are part of this differentiation rules umbrella, but there's also ones that are a little bit more advanced, like product and quotient rule. There's another one called chain rule as well, but they're all differentiation rules. They're all just rules that you use to figure out derivatives. Okay, so a large part of the unit is going to be using those rules to figure out derivatives. And then last but not least, how are derivatives of implicit functions found? If you remember what an implicit function is, it's a function that you can't isolate the y. You can't have it say y equals. So we're going to be able to figure out the derivative of functions that have that. It should say probably more equations than anything, implicit equations, because sometimes they're not actually functions, but that's okay. It doesn't really matter for this slide. So essentially, we're going to be able to answer all of these questions. That's why they're essential questions. Cannot answer them by the end. Make sure you ask. Make sure you get help so you know it's expected of you, but you should be able to answer all those questions by the end. Here is a breakdown of the entire unit, including all of the sections here. So yeah, 2.1, so secant lines versus tangent lines. Secant lines are based off 2 points, tangent lines are based off 1. We're going to talk about that first in this video. Differentiability, what makes something differentiable or not. Estimating derivatives at a point, that's probably the easiest section in this whole thing. So you're just basically finding slope of 2 points and using that to estimate the derivative at 1 point. 2.2 is all rules. Okay, so if you notice right here, every single one of these, it says derivatives of algebraic functions, transcendental functions, product rule, chain rule. These are all just derivative rules used to figure out the derivatives of some function. And last but not least, we're actually only covering 231 for this course because it's Calc 1. Anything where you see like a double star like that, that means it's Calc 2. It's covered in Calc 2. It's still linked on my website. I still, make videos for it and that sort of thing. So if people want to get ahead, they totally can. But we're not going to be covering 232 to 234 because that stuff's all covered in a Calculus 2 course. But we will be covering 231. So that's basically an intro to what Unit 2 is all about. Hang tight, and we're going to start breaking down all these sections, starting with 211. All right, this first section is going to be all about secant lines and tangent lines. And the best way to explain what these terms mean is just with the picture. So let's define these first. So 211, we have a secant line picture and a tangent line on this graph right here. The secant line is the red. Okay, so it's this red line right here. And if you notice, it is based off of 2 points. Now, the tangent line, on the other hand, is just based off of this 1 point. It kind of just grazes this 1 point right here, and that's the tangent line. Okay, so secant line is based off 2 points, tangent line is based off 1. If you were trying to find the slope of a secant line, that is just the standard slope equation. So delta y over delta x. Okay, change in y over change in x. Tangent line, on the other hand, if you were trying to find the slope of this, that's just equal to the derivative. Okay, so that's just equal to the derivative. Slope of a tangent line means derivative. Okay, so I have the equation right here. So slope of secant line, slope is equal to change in y. This is essentially just one of the y values here, and this is one of the y values here with different x's, and then the change in x is on the bottom, as you can see. So that's slope of a secant line, average rate of change, old school stuff that you should know already before taking this class. The limit definition of derivative looks like this, and there is a lot to break down in here, so definitely buckle up here. Okay, first thing here is you'll notice that it says f with this little line here. That line means prime. So this translates to this f prime of x to f, what I just said, basically. F prime of x, it means the derivative. You could also write it as y prime if you wanted. It means the same thing, though. It's just the derivative of y. Another interesting notation is this dy over dx. It is important to understand that this d is not actually a variable. Okay, it's actually a fancy way of writing delta y over delta x, but it's approaching infinity. It's getting infinitesimally closer. So instead of the deltas here, they just replace them with d's. But you cannot just cross out these d's like they're variables. Okay, so dy over dx just means the derivative of y. Another way of looking at it is if you just do d over dx, this is the derivative operator. So you're doing the derivative of y. That's what this means. This is the derivative of y. But what they do usually is they just put the y right up with the d on the top there. So it's dy over dx, okay? So there's many different ways of writing derivative, f prime, y prime, dy over dx. It all means the same thing though, and it's all used interchangeably, so make sure you know all of them. You can't just know one more than the other. Math's a language. You have to be able to, translate it to an understanding in your head. And in this case, it means the derivative. If you remember derivatives definition, going back to that first part of the video, derivative is the slope of a point. So we're just finding instantaneous rate of change, a slope of a point. Slope of an instance in time. Okay, this limit part here, though, is going to be a little bit new here, but it relates back to the slope of 2 points. In essence, this h right here is just a little nudge. Okay, so there's an x value and it nudges over a little bit. So there's this plus, this tiny value, and h is approaching 0. So it's getting infinitesimally closer to x plus h right here is getting infinitesimally closer to this x right here. So x plus h is actually approaching x in a way, because this h part right here is getting smaller and smaller and smaller and smaller. Okay, so in essence, that top part is, it's 2 different points, but they're getting infinitesimally closer together. This bottom right here, you're just dividing by h. Well, h is approaching 0. So if you did direct substitution on this, you would end up with 0 over 0 on this, which if you use limits, again, there is going to be an answer for this. And this is essentially what we're going to use to figure out derivatives. Okay, there's also rules that are going to make it a little bit easier, so you don't have to use this limit definition, but you still have to understand where it comes from and understand how to apply it. Okay, one thing I do want to talk about is this h on the bottom, because it's a little tricky. Why is there an h on the bottom? The top is definitely a change in y, because it's an f minus another f. That's a change in y. But why is there an x on the, or why is there no x's on the bottom? It's just the h. Well, really what you can do is you can have x plus h minus x. So now it actually is a difference of x on the bottom. Okay, it kind of matches what we had previously in the previous slide right here, x minus x sub 0. So it's 2 different x's. Well, if those values are getting infinitesimally closer together, you could just do x plus h minus x, because h is approaching 0. Well, if you do that, the x minus x cancels and you just end up with an h on the bottom. So even though it doesn't look like there's an x on the bottom, it's there. It's just invisible because it subtracted out. So that's why there's just an h on the bottom. Let's move on here to the next one. There's another alternate limit definition of derivative here. Again, same notation, f prime of x, y prime, dy over dx is equal to. Now in this case, x is approaching a. So now this actually is the old school slope definition that we normally use. Only this time the x and the a are getting infinitesimally closer. I should just say the x is getting infinitesimally closer to the a value. So if you did direct substitution here, that would be a and this would be a, and you would end up with another 0 over 0, which is great because that means we can use limits to figure out the value. Okay, but it means the same thing. It's still change in y over change in x. It's just the x and the a are getting infinitesimally closer. So the y's are getting infinitesimally closer, the x's are getting infinitesimally closer, and you end up with some value from that. So make sure you understand this limit definition of derivative as well. Okay, one has an h, the other one has like an a value in there, but they mean the same thing. It's just 2 values, two x values and 2 y values that are getting infinitesimally closer together. Okay, there's another notation here that's kind of annoying. It's for second derivative. Okay, it looks like it says d squared over dx squared. That's actually not what it means. It just means the second derivative. If you did the derivative of the derivative, you would end up with what's called the second derivative. Another way of writing this too is y double prime or f double prime. It just means the second derivative. This notation is kind of weird because it looks like you're squaring the d, but again, d is not actually a variable, so you're not actually squaring it. Where this comes from is if you did the derivative of y, you end up with dy over dx. Okay, well let's do the derivative of this derivative right here to get the second derivative. So we're going to repeat the process, the derivative, only this time we're doing the derivative of the derivative. And if you remember, we just talked about this a second ago, but this right here it means take the derivative of whatever's after it. So this means take the derivative of whatever's after it. It's the derivative operator. Okay, well if you do the derivative of the derivative over here, you'll notice that you could, if you really wanted to, multiply the d's there and get d squared y, and then on the bottom it's dx times dx, which is just that dx squared. Really, I feel like there should be parentheses here, but that's a whole nother story. So that's where the notation comes from, but it's still not d squared and it's not dx squared. It just means the second derivative. I don't really like the notation personally, but that's what that means. Make sure you understand it. D squared y over dx squared, it really just means second derivative if nothing's actually being squared, because they're not actually variables. Okay, you can do derivatives in your calculator. I'm going to show you this a little bit later. So you can see right here in your TI-84, there's this d over dx right here of x squared at x equals 3. You can plug that in your calculator. It's going to do the derivative of x squared, because x times x is x squared at 3, and you get a 6 out of it. So it actually, your calculator will tell you the derivative at a specific point, at a specific x value. You can also graph x squared, but you can also graph its derivative right here. You can graph its second derivative, and then it all shows up on the same screen. I'm going to show you this in more detail a little bit later, but the calculator definitely helps on certain problems, especially if, you know, it's just a little bit easier than doing it by hand on some of the problems. You still have to do a lot of the finding the derivatives by hand, but it's good to check it with your calculator. All right, so this is going to be a video on how to use your calculator to find derivatives at a point. It will not actually find a derivative function overall. You can graph a derivative function overall, but it will not actually help you find the actual derivative, but it will help you find the derivative at a point. So first thing I'm going to do on this home screen, the main screen right here, is say I wanted to figure out the derivative of x squared at x equals 3. What you can do is you can hit Math 8. The 8th choice right here is this n deriv, or you can just hit Math 8. You can scroll down and hit enter on that 8 choice if you want. But it's easier just to hit Math 8. So just remember that Math 8 is your friend when you're trying to find the derivative at a point. Okay, say you're trying to find the derivative with respect to x. This first part right here is actually the derivative operator. It says d over d, and then there's a blank here. Well, we're doing it with respect to x, so I'm going to put an x right there. And we want to do the derivative with respect to x of x squared. So I'm just going to write an x squared in here. Okay, the derivative of x squared is 2x, which if you haven't gone through that yet, you're going to want to make sure you understand power rule on how to find that derivative. But for this purposes, just know that you can find the derivative of x squared. It is equal to 2x, but you have to find it at a certain point. So say we wanted to find it at 3. Because the derivative of x squared is 2x and x is equal to 3, 2x becomes 2 times 3, which ends up being 6. So if you hit enter on this, you should get 6, which means that is the derivative at that point. So the derivative of x squared at x equals 3 is 6. Now you don't have to do x squared. You can do any derivative you want. So say I did the derivative with respect to x of, I don't know, x to the third, I don't know, plus 2x minus 1. It doesn't really matter what you do here. And I want to find the derivative at negative, I don't know, 2. Doesn't really matter. And you can enter on this and it just kind of outputs that value. Sometimes when you input a value like this, you'll end up with something like, it says right here, 14.000001. Okay, you have to basically know to ignore that 0.000001. What essentially what this is doing is your calculator is counting to figure out the derivative rather than actually like figuring out the derivative and then plugging in the negative 2. So you have to kind of use your brain, your human brain on this to understand that that extra change, the 0.000001, is just to be ignored. Okay, so whenever you have a value that's like a little bit of a higher power, or just whatever reason for the derivative to come out in a weird way, sometimes it brings out those extra values there. You have to know to kind of ignore that. Okay, because again, the calculator is not finding the derivative and plugging in negative 2. It's just finding the derivative numerically, and sometimes there's a little bit of counting error in there. It happens sometimes, other times it doesn't. Just make sure you know to ignore it when that does happen. Okay, to graph a derivative, if you hit the y equals right here, just let's say we wanted to graph x squared. Okay, and what I'm going to do is graph the derivative. I'm going to do it in y sub 3 here. What you can do, and this is kind of cool, you can hit Math 8, and we're going to do the derivative. So the derivative shows up here, the derivative operator, d over d. We're going to do d over dx. Now I want to put x squared here, but instead of having just x squared here, what you can do is just put this y sub 1. So it says y sub 1 here. If you hit vars and then arrow over to the right and it says function, you could pick whichever y value you want. So say I wanted to do y sub 1 here, and now it's going to do the derivative of whatever is in y sub 1. So if I change that to x to the third, it would be finding the derivative of x to the third or x to the fourth, or any function, sine x, it doesn't matter. it would find the derivative of that, and you don't have to write it in two places. It just kind of shortcuts it a little bit. And this one, right here, it would actually find the derivative at a point if you put a number in there. But it's kind of weird. If you just put an x in here, it treats it like an x variable. It doesn't really make much sense because it says x equals x. It's kind of weird. But the way this calculator is programmed, this does actually work. Where if you graph this, so I'm going to hit graph right here, you'll notice it graphs the x squared, so there's the parabola, but then it also graphs the derivative of x squared, which is 2x. It takes a little bit longer because, again, it's counting to figure out the derivative of each of those points. And there is the 2x. Value that I was just talking about. The derivative of x squared is 2x. And again, if you don't know how to find the derivative of x squared yet, we're going to be going over that later on in this video. But just know that you can graph the original and the derivative on the same screen with this. If you wanted to, you can even do the second derivative. All right, so if I go to here to this y sub 4 and I do a math 8 again to get that derivative operator there, d over dx. Now I'm going to do the derivative of the derivative here. Well, the derivative is y sub 3. So I'm just going to do y sub 3 in the vars here. So vars, arrow over to y, vars. So vars just means variables. Function, and then we want the third choice, y sub 3. So it's going to find the derivative of that. Hit x equals x here. Well, now the derivative of 2x is 2. So what this should happen is it should graph y equals 2, which that's what that is right there. And again, if you don't understand derivatives yet with how to calculate them, we're going to be doing that later on in the video. Just know that the derivative of x squared is 2x, so it graphed 2x. The derivative of 2x is 2, so it's graphing y equals 2. So that's basically how to use derivatives in your calculator at a point, as well as make them graph. It does come in handy sometimes when you're doing certain problems. So yeah, if you have any questions on this part, definitely let me know. Okay, next we're going to talk about this derivative applet that I found online. Here's a screenshot of it, but I'm actually going to show you what this looks like on the actual website. So all right, so here's a graph, and then there's a point right here on the graph. You can move this point wherever you want. Let's actually just keep it, let's just keep it right here. It doesn't really matter. And what you can do is over here, show tangent. If you click this right here, you can actually show the tangent line on there. So it's just grazing it at that point, and you can move this, and it's going to show the tangent line anywhere you want it to, and it's always just going to be grazing at that one point. It just kind of skims the edge of it, and there's a slope for it. If you wanted, you can show the slope value right here. It kind of gives you a little breakdown of what the slope is based on change in y over change in x. It makes that triangle. I'm not really going to worry about that so much right now. And then it says right here, show slope value as a function value, so I can have that right there. And as you move it, as the slope changes, it just makes it a y value. That's not so important right now. I'm going to turn that off. Trace is kind of cool because what you can do on this is you can actually move this, and it's going to trace out the derivatives for each one. So each derivative here has a value. I'm actually going to have this right here. You can see the value changes as it goes, change in y over change in x. It's a bunch of different values. Well, what if I plotted all these values for each instance? So let's actually do that. We're going to hit show trace. Now watch this. You can actually plot out all those points. Okay, I kind of went too fast there. Kind of skips around there. You can do this here. Still plotting out those points right there. And then you have some function. It looks like it's quadratic, which is interesting because the original function here is cubic, and its derivative comes out to trace to be like some kind of quadratic thing here. You can actually just show the derivative right here, so 3x squared minus 2, and you can actually see, even if I don't have the tracing attached to it, so you can see the tracing there, but right here if I hit show derivative, you can kind of see it also puts the line in there, so you can actually see the derivative on top of it. So one thing I want you to do, what I want you to see out of this whole thing is that a derivative is a function just like the original function. So we have that x to the third minus 2x right there, and its derivative itself is actually a function right there of 3x squared minus 2. So you can kind of see all that there. The tracing just kind of shows each point, but if you want, you could just kind of graph the derivative as well. So just keep that in mind. The derivative itself is also a function. It's just the instantaneous rate of change for each point of the original function. So I'm going to kind of show that again. So if I hit this trace thing, at this point right here, the slope value is 1.74. So if you notice, f right here has a 1.74 value. You can kind of see it there a little bit. That's 1.74. And if I move this over this way a little bit, you can see that this changes 2.2. So if you notice, this one right here is actually 2.2. Every single value is going to have a different slope because the tangent line has a different slope. Now, some of it is the same. Like for the example right here, you can make it where it's 0. If you notice right here, the slope of the line is basically 0. It says negative 0.01 because I can't get it to be 0. But if you notice right there, it's basically 0. Here, if you made a tangent line right here at this top of this peak right here, it's also 0. So I can move this over here, and you'll see that it's also 0 right there about. It's hard to get it exact on this, but you can kind of understand from there. If you plotted all these points out, you have a derivative, or you can just click this and it actually makes the derivative function for you. So the main thing I want you to see on this is the derivative is a function, and every single point has a slope, and if you plot that out, then you get the derivative function from that, from those slopes of all those little individual points. Let's do some example problems to kind of solidify our understanding. This is definitely a lot to go over, so hopefully this helps make sense of it. All right, so it says right here, shown above, even though it's not above, it's right here, that's okay, is the graph of a differentiable function f. Okay, so this thing is f right here. It's labeled with this little arrow right here. Along the line tangent of the graph at x equals 2. So there's a tangent line at x equals 2 right here. You can see it grazes it right there. What is the value of f prime of 2? Okay, well, f prime of 2, if you were going to translate this to English, just means at x equals 2, what is f prime? Okay, well, f prime is the derivative of f. Well, really what it's saying is that x equals 2, what is the derivative? Okay, well, derivative means slope of a point, or instantaneous rate of change. So what is the slope of this point right here? Well, what you can do is just use the slope of this line. There's an equation of a tangent line right here. There's that line there. Well, what's the slope of that line right there? Well, you can see it goes up 1 over 2. So that means it goes up 1, the change in y is 1, the change in x is 2, so it's 1 over 2. So the answer for this one should be A. Okay, that's example problem 1. Here's example problem number 2. So this one's a little bit more of a deep dive into the concept of derivative. So definitely make sure you pay attention on this one, because this one's going to be a little more confusing than the one we just did. All right, an equation of a tangent line to the graph of the differentiable function f. So differentiable just means the derivative exists. Okay, so if something's differentiable, the derivative exists. Differentiable function at x equals 2 is 9x minus 12. Okay, so before in the other problem, we just had an equation. We had this line that's already there. There's a certain equation of that line if you really wanted to figure it out. The slope is 1/2, so you can just say it's y equals 1/2 x plus 2 in this case, because the y-intercept is 2. So there is an equation of that line. We just didn't really need it because we were just looking for the derivative, which was that 1/2. This one, though, it's saying that there's a 9x minus 12 for that function. So what I'm actually going to do is graph this out. So when in doubt, graph it out. It kind of paints a mental image in your head of what this looks like. So first thing I'm going to do is do that 9x minus 12. Let's see here. So I'm going to say this is negative 12 here because that's the y-intercept. So that's the 1 point there. And it's got a 9 slope. So let's just put in, I don't know, at x equals 1, it doesn't really matter. Let's just do 2 because it's already in the problem. So if I put x equals 2 in there, the value for this should be 6, because if I put 2 in there, it's 18 minus 12 is 6. I'm going to connect these dots real quick. All right, so there is our tangent line. Okay, there's an equation of that tangent line. It's 9x minus 12, and we're trying to figure out which of the following must be true. And it is important to note that with these must be true problems, all you have to do is come up with one scenario where it's not true, and it doesn't have to be true. That must means it's always true no matter what. So if you can come up with one example where it's not true, then it's not must be true anymore, so it wouldn't be the answer. So we're looking for the ones where no matter what, you cannot change it from being true. That's one important distinction on this. Okay, an equation for the line, so it's tangent to that at x equals 2. I'm actually going to make that differentiable function f, and I'm just going to make basically a dummy graph that's tangent to this. So I'm just going to do something like, I don't know, like something like this. I'm going to do something like, I don't know, like that. It doesn't really matter. So it's tangent at that point, and then I'm just going to end the function. And then I'm just going to end the function over here like this. It doesn't really matter. So that's what f is looking like. Again, I just made just some dummy graph. It doesn't really matter what you make. It's just to get an idea. This function can look like anything as long as it grazes at this point right here. That's the main thing, is that it grazes at that point because that's what it says it has to do. Okay. And that orange function I just drew is f. Okay. And we have the tangent line right there for f, and let's try to answer this right here. So f of 0 equals negative 12. Okay, well here's f right here, and f of 0 is up here. Okay, it doesn't have to be negative 12. It could be, but it doesn't have to be. Remember, it says must be true. This does not have to be true. Okay, because you can see right here I made it, I don't know, 4 or something like that. I did not make it negative 12. I could have, but I didn't, so it's not must be true. It's not the answer for that Roman numeral 1. Roman numeral 2, f of 2 equals 6. Okay, f of 2 has to equal 6 because there's a tangent line there. And if there's a tangent line there, then the graph, the orange, the f, has to be there as well. So this actually does have to be true. Okay, so I'm going to circle that. That definitely has to be true. And then the next one, it says f prime of 2 equals 9. So that means the derivative at x equals 2 is equal to 9. Well, the derivative at 2 is equal to 9 because the slope of the tangent line there is equal to 9. So that would be true as well. So the answer for this one should be C, both Roman numeral 2 and Roman numeral 3. All right. That concludes our first section here of this unit. The next section is going to be a further deep dive into these concepts. All right, this next section is going to be about differentiability, and differentiability is just, if something's differentiable, it means the derivative exists at that point. If it's a differentiable function, then it's differentiable on all the values of x in its domain. So that's what differentiability is all about. It's just the ability to be differentiated, the ability to find the derivative at that certain point or overall in the function. In order for something to be differentiable, certain things need to be true. Namely, it has to be continuous. Okay, so there, both of these equations must be true in order for a function to be differentiable at a point, but what do they mean? This, hopefully, you understand, is just the limit definition of continuity. Okay, it was from the last unit. Okay, you still need all the stuff from the last unit for this unit, but if you remember, limits help define continuity, and you have to be continuous in order to be differentiable. If you are not continuous, then you can't be differentiable because there is no point there. Okay, if there's no point there, how can you take the derivative at that point? That doesn't make any sense. So it definitely has to be continuous at that point. So that's the first key concept on that, is it has to be continuous. The next thing, the bottom thing, is if you notice, it's the limit definition of derivative, but it's the limit definition of derivative on both sides. The limit definition, the derivative of a function has to agree on both sides. That's what that's basically saying. The bottom equation is saying the derivative has to match on both sides. So I'm going to write that in here. So the derivative must match on both sides. And if it doesn't, then it's not differentiable. If it's not continuous, it's not differentiable. A really important concept to understand, if something is differentiable, then it's automatically continuous. Okay? Because if it's differentiable, it has to be continuous to begin with. So if it's differentiable, then it's automatically continuous. However, if it's continuous, it's not necessarily differentiable because of this second part right here where it says the derivative must match on both sides. Okay, so in order for that to be true, the derivative has to match on both sides. In order for the derivative to match on both sides, it can still be continuous and the derivative not matching on both sides. So in order for it to match on both sides, it has to undergo what's called local linearization, and I'm going to show you an example of that in just a second. But just make sure you understand, if it's differentiable, it's automatically continuous. If it's continuous, though, it's not necessarily differentiable, and I'm going to show you an example right now. All right, before I show you that example, though, I'm going to show you this comic right here that I think is pretty funny. It says, what makes hills in the road flatten out when we get there? So this kid is asking right here, this adult right here, how come it looks curved, but as soon as we get there, it looks straight? This is actually the idea of local linearization. So it's kind of an awesome comic. It fits well with calculus without even realizing it. So right here, it says local linearization and differentiability. And what we're essentially going to do for this is we're actually going to look at the graphs of this rather than just looking at this still image. So first, let's look at this graph here. So here is the graph of x squared right here in red. And what we're going to do is we're going to zoom in on this graph and see what happens as we zoom in. Okay, it's kind of like that comic that we just talked about a second ago. The person is saying, how come when we get there the road is flat even though it looks curved from far away? It's also the reason why a lot of people think that the Earth is flat, because it seems like it's flat because we're so zoomed in. But if you actually like took a step back, you'd be able to see that it was more curved. It's called local linearization, and I'm going to show you. Hopefully, this helps make more sense of it as we're going over it. So right now, what I want you to do is just kind of guess. You can even pause the video here after I ask the question to kind of think about it for a second. But what happens if I actually zoomed in at, let's just say 0, 0? That's where the maximum curve is here. What happens if I actually zoomed in at 0, 0? What would that look like? What would we be seeing as that happens? Okay, so pause the video, think for a second, and then I'm actually going to zoom in so you can kind of see it. So pause here. All right, hopefully you pause, because what I'm going to do here now is zoom in at 0, 0. Here we go. Hopefully you guessed correctly. If not, that's okay, because then you're going to learn something. So we're going to zoom in here. Notice what happens to the graph. It appears to basically be flattening. Okay, it appears to just turn linear. Okay, now zoom out again. You can kind of see that. Now this does it anywhere. Okay, it does not have to be 0, 0. It could be anywhere where there's a curve. So for 1, 1, you can see it's a curve there. But as soon as I zoom in, now it just looks like a line. It looks like a straight line right there. Okay, zoom out, you can kind of see that it's not. Same over here, I can zoom in here. Doesn't look like a line, doesn't look like a line, but now all of a sudden it looks like a line. And this can happen anywhere. Anytime you have a differentiable function, this is what will happen. Okay, you can take any curve and zoom in, and you'll see it appears to flatten, and now on the screen right here, it just looks like it's a line, but really it's not. You can zoom out and see that it's not a line. Okay, so it just kind of flattens. I thought that was kind of a cool, concept to look at with differentiability. It has to flatten out. Now, this flattening out is because the derivative matches on both sides. The slope on both sides matches. It approaches a specific value. So if I zoom in right here, the slope approaches both things. It's whatever the slope of that line is right there. Same with this right here. If I zoom in, it looks like the slope's going to end up being 0 because it just flatlines. Okay, not all graphs do this. And even if it's continuous, which x squared is continuous, it still doesn't always happen. Okay, so what I'm going to do is compare it to this absolute value of x. Now I want you to pause the video after I ask the question and answer it. What happens if I zoom in at 0, 0 right here? Okay, is it going to flatline again? I don't know. Let's check it out. Okay, pause it here, make a guess, and then we're going to go over it. Okay, here we go. We're going to zoom in at 0, 0. Here we go, and this is not a trick. I'm zooming in right here, and you can notice it does not change at all. Okay, because it doesn't become linear, it's not differentiable. Even though it's continuous, it's defined at all the x's. It is a continuous function. It follows the limit definition of continuity. But if I zoomed in here, it does not flatline. It does not become a line. It just stays looking like this. When that happens, then it's not differentiable. Okay? And the reason for this, if you actually break it down, the derivative on one side is like -1. The derivative on the other is +1. They don't match in the middle. Okay? They're not approaching the same value. From the right side, the derivative is +1. From the left side, it's -1. It does not match. So because of that, it doesn't flatten out. Okay, I can show you with this one here just so you can kind of see that it's not a trick. I'm going to zoom in here. You'll notice the x squared starts to flatten. It agrees on both sides. It becomes linear. It's differentiable with the x squared, which is in red. The blue, however, it's not differentiable and never becomes locally linear. Okay, now it does over here. Like if I zoom here, then yes, it's a straight line. It's differentiable at other x values. It's just not differentiable at x equals 0. That is an important distinction to understand too. It's differentiable all over here and all over here because the derivative matches on both sides and it's continuous. But here, the derivative does not match on both sides even though it is continuous. All right, last but not least, we have the x to the 2/3 power. Okay, holy cow. So now it's curved, but there's also a sharp turn as well. So how do we answer this? Okay, well, first of all, I want you to guess on this. Pause the video and guess what would happen if I zoomed in at 0, 0 right here. So pause here and then we'll go over it. Okay, hopefully you came up with some idea here. Here we go. I'm going to zoom in, see what happens. Uh-oh. Uh-oh. So it looks like it becomes linear, but it's a vertical line. Okay, this is another instance of something not being differentiable. You cannot have a vertical line because the slope would be infinity, and if that happens, the slope would be undefined. If the slope is undefined, then it's not differentiable. So that is another important distinction to take into this is whenever it's a vertical line with the derivative, with the tangent line, if it's a vertical tangent line, the derivative does not exist at that point. Okay, other curves though right here, let's just say x equals 2. You'll notice if I zoom in here, it becomes a straight line. So it's differentiable there. It's differentiable, here because it forms a straight line again. It's just not differentiable in the middle because you end up with an infinite slope, and you can't have an infinite slope. So the moral of the story that you can take away from all this is if there's ever a sharp turn, which is not a mathematical term, but if there's ever a sharp turn, a cusp, then it's not differentiable. Okay, so you can see right here, it's not differentiable at x equals 0 because there's a sharp turn for both of these right here, where the x squared, it's not a sharp turn, it rounds off the entire time. So as you zoom in, one of them will flatten, the other ones will not. X squared is differentiable, the other ones are not. So that's essentially what that slide was showing. And again, make sure you write it down. If it's a sharp turn in the graph, it's not differentiable at that point. Super important to understand. All right, let's look at an example problem right here. Which of the following statements, if true, cannot be used to conclude that f of 0 exists? Okay, first thing I'm going to do is get rid of this word exists. I should write is defined. Okay, that exists is a little problematic because limits exist. Values of f are defined. Now, exist might work in this. I'm just being a bit extra on that, but that's okay. It doesn't really matter. So which of them, if true, cannot be used to conclude that f of 0 is defined? So what I'm going to do on this is actually, because this is, that's a lot of concepts on this problem. What I'm going to do is actually just graph this out. Okay, f of 0 exists, so I'm just going to say f of 0 is right here. Doesn't really matter the value for it, so there's some y value there. It exists. Okay. So if this is true, so if this limit right here is true, as the limit approaches 0 on both sides, it cannot be used to conclude. Well, let's just break this down here. Here's a graph right here. The limit approaches both sides at 0, and it does show that f of 0 exists. However, I could have actually made this a hole, and it still would have worked. So this kind of gives away the answer right away. A is still true. And you cannot conclude anything about f of 0. Okay, so it says if true cannot be used. This would actually be the answer. You cannot actually use it to conclude the other things. So that's not very exciting because it just kind of gives away the answer right away with A. So let's actually go over all of the other ones as well. So first thing I'm going to do is fill in this hole right here. Again, because it says f of 0 is defined. Okay, it says right here, if f is continuous at x of 0, is f of 0 defined? Yes, it has to be. If it's continuous, there has to be this value filled in here. It cannot be a hole like I just had before. So if true, it says it cannot be used to conclude. The question is asking cannot be used to conclude. This can be used to conclude, so it's not the answer. So we're looking for the one that's not. So this is true, but we're looking for the one that's false, which is A, which we already covered. Okay, C, if it's differentiable at x equals 0. Okay, if it's differentiable, that means it's continuous. If it's continuous, that means the point does exist. So again, that is actually true, but we're looking for the one that is not true. It cannot be used to prove it, so that would be C. And then D, it says the graph of f has a y-intercept. Well, that is the y-intercept because it's f of 0, so that means that's also true. So the only possibility that works is A for this one. Just because the limit of f of x at x approaches 0 exists, it doesn't mean that f of 0 has to exist. It could be a hole. And if it could be a hole, then it's not the answer. Okay, because you're looking at all possibilities. The other ones, B, C, and D, if those are true, then you have to have f of 0 existing, or in this case, is defined. Holy cow, that's a lot of concepts. That's crazy. Okay, the second example problem right here. It says the function h is defined in the closed interval -1 to 3. Okay, you can kind of see that on the graph. It goes to 3 here, and then it's -1 here. So it's h, it's defined here. The graph of h prime, the derivative of h is shown above. So this is the derivative. It's not actually h, it's the derivative of h. That is really important to understand. Make sure you know what you're looking at. This is actually h prime. I'm actually going to write it here, even though it says it on the bottom, just for fun. Okay, the graph consists of 2 semicircles, so 2 half circles. You can kind of see them here, like one's right here, that's clearly a half circle, and then the other one's right here, that's the other half circle. And a common endpoint at x equals 1, right there. Which of the following statements must be true? Okay, so must be true. If you can come up with any possible way of making it so they're not true, then it's not the answers. Okay, so let's look at this here. Roman numeral 1, color code this here. H of -1 is equal to h of -3. The problem with this is we have no idea what h is. Okay, we do not, it doesn't show what h is, it just shows what h prime is. So because of that, it's not necessarily true because we don't really know what's going on with h. So you can't say that it is true or not because we don't know. So which of the following must be true? That doesn't have to be true because we don't really know the function to make a decision on that. We know h prime, we don't know h. Okay, now you might be tempted to go, but look, the endpoints, here's h prime of -1 and h prime of 3. Those are the same. Just because those are the same does not mean h is the same. Because remember, the graph is of h prime, not h. If it said h prime of -1 is equal to h prime of 3, then yes, that is true. Okay, but it's not saying that because this one has primes, this one right here does not. Okay, so that's why it's definitely not Roman numeral 1. Okay, Roman numeral 2, h is continuous at x equals 1. Okay, we don't have h. Again, we don't know what h is, but we know that it's differentiable at x equals 1 because the derivative exists. It's right there. This is the graph of the derivative, and there's a point there. It's not a hole, a jump, a gap, or anything like that. It's defined there. So that means this has to be true. It must be true because the derivative has a point at x equals 1. That means h has to exist. If h prime of 1 exists, h of 1 exists. The next one here, let's see, the graph of h as a vertical asymptote at x equals 1. That is actually impossible because if h had an asymptote right here, then there would be no derivative here. Okay, the derivative actually exists there because the graph of h prime is there. So because there's a derivative there, that means there can't be an asymptote there, because if there was an asymptote there, then you couldn't have the derivative because asymptotes are discontinuous. So it's not that one either. So the answer for this one is B. So that is the concept of differentiability with 2 example problems. Hopefully that solidified your understanding on this a little bit more. If you have any questions on this section, definitely let me know. And now we're going to go on to the next section. All right, this next section is going to be all about estimating derivatives at a point. It's not really a lot of calculus on this besides like using the fact that there's the word derivative in there because it's just going to be basically finding the slope when the derivative, you don't have enough information to find the actual derivative. So it's very algebra based. This is probably going to be the easiest section in this unit, as I said before. But that being said, don't sleep on it. Make sure you definitely understand how this all works. Okay, so the main premise is right here. It says, estimating derivatives. When you cannot find the derivative at a point, use points around that point. So say we're trying to figure out the derivative at a specific point, I don't know, let's just say x equals c. Okay, what you can do is use points that are around x equals c to estimate the derivative at that point. That's essentially what you're doing. So you're using the old school average rate of change to estimate the instantaneous rate of change. That's basically all there is to it with this concept. I'm going to show you an example right here from AP Calculus. And it's got a table right here, and it's kind of color-coded. So it says years in meters, and it's got these 2 right here circled in orange because the problem is saying estimate h prime of 6. Okay, well there is no 6, but 6 is between 5 and 7. So what you can do is just find the slope between 5 and 7, which is what I did right here, to get 5 over 2. Okay, so that's essentially what you're supposed to be doing in this. You're finding the derivative, but that point is not in the table, so you just have to use the points that are around it. 5 and 7, in between 5 and 7 is 6. So if you do the slope between 5 and 7, t equals 5 and t equals 7, and you find that slope, it estimates the derivative at 6. Okay, that's an example that's already worked out. Let's actually do an example that's not already worked out so we can kind of get a further understanding of this concept here. Okay, it says, unless otherwise specified, the domain of the function is assumed to be a set of all real numbers x for which f of x is a real number. Okay, so just saying that it's defined everywhere doesn't really matter too much. The number of gallons of olive oil in a tank at t is given by a twice differentiable function. Okay, twice differentiable just means that the second derivative exists as well for this function a, where t is measured in hours from 0 to 35. So you can kind of see it goes from 0 to 35 in this table. Values of a of t are given right here. Okay, so if you want, you can think of it, this is x and this is y. Okay, only it's t and a of t, but you get the same idea. It says, use the data in the table to estimate the rate at which the number of gallons of olive oil in the tank is changing at t equals 10 hours. Okay, so we're trying to figure out what is a prime of 10. Okay, but we're estimating it, so I'm going to write the estimation symbol there with a question mark. Okay, show computations that lead to the answer, indicate units of measure. Okay, so we're trying to figure out a prime of 10. But the problem with this is we don't have an a equation, we just have the table. So what we can do is just use the values that are around 10. In this case, 5 and 15. Because in the middle of 5 and 15 is 10. So what we're going to do is we're going to do the slope of these right here. Okay, so it's change in y. So we're going to do 25 minus 18. That's the change in y. Over the change in x, which is going to be 15 minus 5. Okay, 25 minus 18 is 7, 15 minus 5 is 10, so the answer you get is 7 over 10. Okay, but it says show the computations. I did that. Indicate units of measure. Well, it's just change in y over change in x, so it's gallons over hours. So it's just going to be gallons per hour. And that's going to be the answer for this one. Okay, onward we go. Let's do another example problem. Okay, the function f is differentiable and has the values shown in the table above, even though the table is below. Both f and f prime are strictly increasing. Okay, so the derivative is increasing and the value of f is increasing as well. Okay, on the derivative from 0 to 5, which of the following could be the value of f prime of 3? Holy cow, this is a lot to break down. All right, first thing that you should see is that f is increasing the entire time. So it's strictly increasing, it's only going up. Okay, its derivative is also going up as well because that's what it says right here. So what we need to do is estimate the derivatives in between all of these points, and I'm going to use a calculator to do that. Okay, so first thing I'm going to do is find the derivative in between these 2 points right here. Okay, so we're going to do 39.2 minus 31.25. You get 7.95, and then we're going to divide it by 0.3 because it's change in y over change in x, and you get 26.5. Okay, I'm going to do the same thing here. So these are estimations of derivatives. The derivatives should be going up here, though. 45 minus 39.2, you get 5.8. Divide that by 0.2, you get 29. Okay, and then I'm going to estimate the derivative right here. 48.05 minus 45 divided by 0.1, you get 30.5. So as you can see, the derivative is increasing between each of these. Okay, the estimation of it anyway is, so it's increasing from here to here to here. It's asking what could the value of f prime of 3 be? So what could the derivative be here at this point right here in between? Okay, well, it can only be going up, so it cannot be 29, it can't be 27.5 or 20, because it has to be between 29 and 30.5. It could be 30. It cannot be 30.5 because then that's equal to it. It has to be between those two values. So the answer for this one is D. But holy cow, there's a lot of concepts in that one. That one's definitely confusing. Make sure you reach out if you have questions. That is the section 213, all about estimating derivatives at a point. Let me know if you have any questions. All right, this next section is going to be all about the derivatives of algebraic functions. Okay, so we're not doing transcendental functions in this section. That's actually going to be the section after this. This one's just going to be algebraic functions. And namely, it's the one that we're going to be covering is called power rule. Okay, power rule basically states the following. So right here, if you have the derivative, remember this means the derivative operator. So this means take the derivative of whatever expression is after it right here. So we're doing the derivative of this thing right here. What I want you to see in this pattern is all you have to do for this is take the n, which is just some constant, c is a constant as well, and you could throw it in front and multiply it by the c that's already there. So it says n times c. And then after that, what you're essentially doing is taking whatever that power is and you're subtracting 1 by it. Okay, this will get you the derivative of any power function. Okay, so say I wanted let's just say that f of x, so here's just an example. F of x is equal to x squared. Okay, what I can do is say I want to find the derivative of this. All I have to do is drop the 2 in front, so it's going to be 2x, and then I minus 1 from the power. So in essence, what this becomes is just going to be 2x to the first power, or just 2x. Okay, so that's in essence what you're essentially doing on this, is you're bringing down the power to multiply it with whatever number is in front. Now it doesn't look like there's a number in front on this one, but there really is just a 1 here, it's just hidden. So you're multiplying the 2 by 1 to get the 2 here, and then you're minusing 1 from the power to find the derivative right there. Okay, so that's basically an easy example of using power rule. Whatever the power is, you just bring it down and you multiply. Okay, onward we go here. I have a video, this is a younger version of me here, a video that actually explains where power rule comes from. When I was a kid, I used to get frustrated when teachers would go, hey, here's a formula, this is what you're going to have to use. It's like, okay, cool, but where did the formula come from? Like, how did someone come up with it? This came from a human's mind. How did they do that? Okay, so I actually broke down where this rule comes from using the limit definition of derivatives. So hopefully that looks familiar to you right there because we just went over that. And then just breaking down the limits using binomial expansion right here for that, working it all out. And you end up with this right here if you started with the actual function of x to the n power, so you end up with power rule there. I will link the video, or actually I'm just going to probably put the video right into this video so you can watch it if you want, but if you don't want to, that's okay. The most important thing is using power rule rather than like knowing where it comes from. I'm never going to ask you, hey, where did power rule come from? That's not as important. What's important is understanding when to use it and how to use it to figure out derivatives. Okay, so let's look at some examples here. It says example problem number 1. We have a piecewise function. If g is the function defined above, g prime of 1 is what? Okay, so g prime of 1. The problem with this is that the x equals 1 is on 2 different pieces. Okay, so what we need to do is actually do the derivative of both of these. So I'm going to call the first one g1 of x, and we're going to do the derivative of this 2 minus 2x, and then I'm going to also do the derivative of that second piece. I'm going to call that g sub 2, which is equal to 5x minus 5. Okay, now we're going to be using power rule for all of these here because it's all, everything is a power on this, a power function. All right, so g prime, so here's g1. I'm going to do g prime, so g sub 1 prime of x. So I'm going to do the derivative of this right here. I'm going to do the derivative of 2 and the derivative of the minus 2x. The derivative of 2 is actually going to be 0. And this is based off of power rule. So if I did the derivative, remember that's a derivative operator, of 2, well, it doesn't look like a power because there's no x with it, but what I can do is just artificially put 1 in to be x to the 0. Okay, x to the 0 would be equal to 1 because anything to the 0 power is 1 unless it's, x equals 0, but you don't need to worry about that. So what we're going to do is we're going to use power rule on this, bring the 0 down. So now it's going to be 0 times 2 times x to the 0 minus 1. Well, it doesn't matter everything after the 0 because 0 times anything is 0. So this derivative ends up being 0. The derivative of 2 is 0. In fact, the derivative of any constant is 0. So you're going to want to use that. It's kind of just a way of using power rule to figure out the derivative of a constant. There's no x value in there, so it's always going to be equal to 2. So therefore, the derivative is equal to 2. Another way of doing it, of figuring out that derivative, is if you just graph it. So that's what I'm going to do. I'm going to graph y equals 2. So it looks like this. Well, the derivative at any point on this, let's just say the point right here, the derivative there, the tangent line is 0. The derivative of this right here, where it grazes that point, is 0. If you notice, the derivative anywhere is going to be 0. So because of that, the derivative of 2 is 0. The derivative of any constant is 0. All right. Now we're going to do the derivative of 2x. So it's going to be minus whatever this derivative is here. So I'm going to write this over here, the derivative of 2x. Okay, this is definitely a power function. There's a 1 up here, so I'm going to bring that down, multiply it by 2, so 2 times 1 is 1, and then we're going to subtract 1 from that power. So you get 2x to the 0 power. X to the 0 power is 1, so we're just going to get 2. So the derivative on this is 2, so it's 0 minus 2. G sub 1 prime of x is equal to negative 2. Okay, but we need to make sure that the derivative matches on both sides. Okay, so let's do the other one here. So for this one, we're going to do the derivative, g sub 2. That's just going to be equal to 5 minus 0, which is just going to be equal to 5. So this one's kind of easier. It's the same kind of thing, though. We have a linear function. The derivative of 5x is 5. The derivative of 5 is 0. So this derivative is 5. So if you notice on one side, it's negative 2. The other side is 5. So therefore, the answer should be non-existent. Another thing we could have started with if we wanted is continuity. Sometimes I jump right to the derivative. Other times I jump right to the continuity for it. But if you remember, for a derivative to exist, so this was covered in the previous section, for a derivative to exist, it has to be continuous and the derivative has to match on both sides. This one does not have a derivative matching on both sides. But it is actually continuous at x equals 1 because if I plugged 1 into this, you get 0. If I plugged 1 into this, I get 0. So it's 0 for both of them. So it actually is continuous on either end of this. It's just the derivative does not match on both sides. Now to show you this, I'm just going to graph this really quick to give you an understanding of what all this means so you can kind of get a visual of it. All right, so we're going to say g of x is equal to, and we're going to do a piecewise function on this. So that first one was x is less than 1. And when that is occurring, it's going to be 2 minus 2x. Okay, so that's the first piece. The other piece is going to be x is greater than or equal to 1. And for that, it's going to be 5x minus 5. So one thing that you should see on this, and this brings up a lot of previous topics that we've covered already, so this is pretty awesome, that it is continuous. It does meet at that point 1. The limit agrees on both sides as well as directly on it. It's 1. or I'm sorry, it's 0 in this case at x equals 1. But it's a sharp turn. So right away, you can see it's a sharp turn. That means the derivatives are not going to match on both sides. In fact, one side is positive 5 because it goes up 5 over 1. The other side is negative 2 because it goes down 2 over 1. So one side is negative 2. The other side is positive 5. The derivative does not match on both sides. It's also a sharp turn, which is going to show you that every single time whenever it's not differentiable. So in this case, it's not differentiable. So that means the derivative at 1 does not exist because at g, it's a sharp turn. All right, so hopefully that makes sense. It also makes sense without what we did when we didn't graph it as well. We just solved it all algebraically. The derivative does not match on both sides, even though it is continuous. So either way, you get non-existent for that. The next example problem, holy cow. This is a lot to break down, and it's easy to get intimidated by this, but it's actually not that bad. The main thing that you need to see on this one is this is the limit definition of derivatives. So I'm going to write that down. Limit definition of derivatives. The definition of derivative. Okay, so we need to figure out what is the actual function that's going on here. Well, if you remember, it's f of x plus h. So the limit definition was as h goes to 0, it's f of x plus h minus f of x. And it's all over h. So this is basically saying what's the derivative of some function, but we don't know what the function is. It's in there, it's just you have to kind of extrapolate that out. In fact, the function itself, f of x, is equal to x squared plus 4x. Okay, you can kind of see that from this part right here where the plus h's are, or you can actually see it right here, but the minus is distributed, so it's kind of hard to see that it's actually plus 4x. Okay, so that's the function, and we're looking for the derivative of that function. Rather than expanding that all out and working it all out, it's easier to just find the derivative using power rule. Now you can use limits to solve this if you want, and you get the same answer. But if you use power rule, this becomes 2x, this becomes 4 using power rule. So it's 2x plus 4, so the answer for this one would be C. Okay, so moral of the story is see that you need the limit definition of derivative to solve this. Figure out what the function is from the actual graph. You can see it. You just basically take away those plus h's, and you can kind of see that f of x function here. Or you can look right here, but then you have to be weary of this negative distributing. Either way, it's x squared plus 4x. Do the derivative using power rule, and you get C. All right, and the last one that we're going to do in this section right here, example problem number 3. Let f of x equal this function right here. What is the value of f prime of negative 1? So what this means is find the derivative and plug in negative 1. Okay, so that's the first thing we're going to do is find the derivative using power rule. So I'm bringing down that 3, multiplying it by the 2 to get 6, minusing 1 from the power. Subtracted by, bring the 2 down, you get 8 minus 1 from the power, so now it's a 1. The derivative of negative 5 is 0. You don't have to put the 0 in there. I'm just going to do it for fun. Next, after you find the derivative, you just plug in negative 1 for all the x's. So that becomes 6 minus negative 8. So you add those together, you get 14. Your answer should be D. So that is power rule, probably the easiest rule that we're going to be covering for this unit, but definitely still important. And all the other rules are still based off of, a lot of them are still based off of power rule, so make sure you understand this. And if you have any questions, definitely let me know. Onward to the next section. All right, so this next section is going to be all about the derivatives of transcendental functions. And transcendental functions, if you didn't know what those are basically functions that transcend algebra. So it's beyond, polynomials, beyond rational functions, that sort of thing. It's things like the following. So right here, derivatives of transcendental functions. You can see we have the derivative of the 3 trig functions right here, sine, cosine, and tangent. We also have the secant, cosecant, and cotangent derivatives as well. And then we also have the inverse trig derivatives of arcsine, arccosine, arctan. And down here, we also have the exponential. So we have the derivative of a to the x. We have the derivative of the logs as well. So log base a of x, the derivative of e to the x, and the derivative of ln x. Okay, so those are the derivatives of the transcendental functions. You are going to want to memorize each of those because you're going to need those to figure out the derivative. So you need to know, let's just kind of break this down here. Okay, so this first one right here, the derivative of sine is cosine. So whenever you see the derivative of sine, then you just know that it's cosine, so then you can write that down as the answer. Same thing with this one, the derivative of cosine is negative sine. The derivative of tangent, x, is secant squared x. Okay, and if you do want to know where these derivatives actually come from, like using the limit definition of derivatives, I do have other videos linked on my YouTube channel that actually show why the derivative of sine is cosine, why the derivative of cosine is negative sine, and so on. Over here we have the derivative of secant x, cosecant x, and cotan x. Again, just make sure you memorize all these formulas right here. One thing I do want you to notice is anything that has a derivative with a co in it is negative. Okay, so let's break that down a little further. So the derivative of cosine x is negative sine x. Okay, the derivative of cosecant is negative cosecant cotan x. The derivative of cotan is negative. So there's that negative in each of the cos whenever it's a derivative. Arc cosine, the derivative of arc cosine x, has a negative in front of it. So that's one thing that kind of helps memorize these a little bit easier, is those cos. Down here with the exponentials, one thing you'll notice is the derivative of a to the x is itself times ln of whatever the base is. And I do have a video that explains why that is as well, if you want to check that out on my YouTube channel. This one's an interesting one. The derivative of e to the x is e to the x. Okay, the derivative is actually itself. And you can kind of deduce this based on the other formula right here. The derivative of a to the x is a to the x ln a. Well, if you use that same formula for the derivative of e to the x, it would be e to the x ln of e. Well, ln of e is just 1. So that just cancels and it's 1, so the derivative is itself. That's kind of why that works out the way it does. And then logs, just make sure you understand these formulas as well. It's the same kind of thing, ln of a. Well, if the a is e, the base e for ln, then it's just ln of e, it's just going to be 1 over x on the bottom. One thing that is interesting on these derivatives, for example, the ln x, is the fact that it's a 1 over x. Okay, so you have this natural log function, and for whatever reason, its derivative is 1 over x. I just think that's super interesting. But long story short, make sure you memorize all of those formulas because you're going to need them whenever you're finding the derivatives. Let's do some example problems. Okay, example problem number 1, let f be the function defined right here. What is the value of f prime of 0? So first thing that you need to do whenever you see this, it says f prime of 0, is you have to find f prime of x first. Okay, once you find f prime, then you just plug in 0 for x, and then you can find f prime of 0. So first thing we're going to do is find the derivative of 3 sine x. Well, the derivative of sine is cosine, so it's going to be 3 times cosine x. The 3 just stays there. The derivative of sine x is cosine x. So we have that first one there. The next one, it's 8 e to the x. Well, the derivative of e to the x is itself e to the x, so it's just 8 e to the x. It doesn't actually change much. So you have the derivative, but we are not looking for the derivative. We are looking for the derivative at x equals 0. So I'm going to plug in 0 for all these x's, and you end up with 3 cosine of 0 plus 8e to the 0. All right, now we need to simplify. Cosine of 0 is 1, so this is just going to be 3 plus e to the 0 is 1, so it's just going to be 8. 3 plus 8 is equal to 11. So the answer for this one would be D. Okay, again, just using those formulas. I have them memorized, but if you don't and you're trying to do these example problems, you can always just look back right here during practice. It's just assessments where you're going to have those memorized. All right, let's look at the next example here. All right, so here's another example problem involving the derivative of transcendental functions. We have f of x is equal to ln of x right here. That's what it's defined. If f of x is equal to that, what is this value? And you might be thinking, wait a minute, why are we doing a limit problem if this is a derivative unit? Well, this is actually the alternate limit definition of derivatives. So you actually are finding the derivative. You just have to kind of look through it, look through that notation basically to see it's not just some limit problem, it's actually the limit definition of derivatives. But there's actually kind of a twist on it as well, is the fact that it's x minus 2 on the bottom, and then at the top it's f of 2 minus f of x. So really what I'm going to do, because it's supposed to match, it should be x minus 2, on the top it should be f of x minus f of 2. So what I'm going to do is I'm going to rewrite it. Okay, so on the top I'm going to flip the f of x and the f of 2, because that's in technically the wrong order if you think of the alternate limit definition. But if you flip those, you basically need to put a negative sign in front of this whole thing. Okay, because if you flip those, essentially if you distribute that negative on the top, you get the same thing that where you started from. So really that's actually equal to this green right here that I wrote down. And what this is actually equal to is if you did f prime of 2. So it's the derivative at x equals 2. So what we need to do here, it's actually equal to negative of the derivative of 2 because of that negative symbol there. Okay, so what we need to do here is find the derivative. So that's the first thing I'm going to do. Well, luckily this derivative is pretty easy. The derivative of ln x is 1 over x. We went over that when we were looking at the formulas over there just a second ago. And then we're looking for the derivative at x equals 2. So I'm going to plug in 2 there. But I'm forgetting that it's supposed to be negative because this one's kind of needlessly tricky with that negative part there. So anyway, you end up with negative 1/2. So your answer for this one is B. So it's definitely tricky because you have to notice the order of that top part, but once you see that, it shouldn't be too bad. So if you have any questions about the derivatives of transcendental functions, make sure you reach out and ask me. That's basically the section for derivatives of transcendental functions. Make sure you memorize all of these formulas because you're going to need them whenever you find those derivatives. All right, on to the next section. Next section is all about product rule and quotient rule, which are basically rules for derivatives when you have a product of two functions or when you have a quotient of two functions. So whenever you're multiplying functions or dividing functions, you're going to want to use these rules for those derivatives. Okay. All right, let's look at these rules in action here. So right here, product rule and quotient rule. This first one, let's zoom in right here so we can just focus on the product rule first. So this first one, if you notice it says the derivative, that's what this thing right here, the derivative operator is saying right there, the derivative of f times g. Okay, so you have the derivative of two functions. And essentially what we're doing is we're doing the derivative of f times regular g plus the derivative of g. So the derivative of f times regular g plus the derivative of g times regular f. And I try to color code it there with the greens and the oranges. For each of these, so you can kind of see it's basically like the derivative of one times the regular of the other plus the derivative of one times the other one. The derivative of the other one plus times the derivative of the regular. It's almost like they switched dancing partners on who's the derivative and who's not. That's essentially product rule. I do have a video outlining exactly where this formula comes from. So if you're just like, whoa, why is the derivative of two functions times each other equal to this? Well, I made a video that's like outlining basically the entire proof behind that derivative using limit definitions of derivatives. Again, on my YouTube channel, if you want to check that out. It's not going to be expected for you to know it for the course, but I don't know. When I was a kid, I always hated when formulas just came out of nowhere and the teacher didn't explain it. It's like, well, how did a human come up with this? So I basically have the proof video if you're interested in it, but again, it's outside the scope of the class to know exactly where it came from. This one here is same kind of thing. We're doing the derivative. That's what this d over dx is, the derivative operator of f divided by g. Okay, now this formula is a little bit crazier. Okay, so we have gf prime here. Code it really quick. So gf prime minus fg prime all over g squared. This one's not too bad to memorize, but it's not as easy as product rule, obviously. One thing that students mess up on is mistaking the order from this to this. They'll either put fg prime first and gf prime second. Order does matter for this because there's a subtraction. With product rule, the order doesn't matter because you're adding. Multiplication doesn't have an order. Adding doesn't have an order. It doesn't matter. Where this one, it does. A lot of times students don't have trouble remembering the g squared. It is kind of awkward though in the formula. Again, if you want to know where this actually came from, you can watch that video on my YouTube channel that explains it. Definitely helpful if you have trouble sleeping. You can always watch the proof for it. One thing that I always try to remember for this is it's gf prime. It's kind of like girlfriend prime. That always comes first. So the girlfriend prime always comes first. The rest of it kind of falls into place because I know the next thing's minus. I know it's the opposite of this first one. So rather than memorizing the whole top thing, just memorize the first half, and then you know the other half is the opposite of it. Instead of gf prime, the other one's fg prime. Either way, however you want to come up with the memorizing for it, that's on you. I wrote this again out only with the f of x and g of x in this case instead of just f and g. It's the same thing though. Sometimes you'll see it in textbooks or online, written like this with the of x for everything, versus the other one didn't have the of x. It's the same formula though, so you don't really need to worry about it. I just kind of wanted to show you that. So let's do some examples, and I'm going to show you kind of my way of solving these. By all means, it's not the best way, but for me, I think it's the best way, but you might not. But I'm just going to kind of show you how I do it. Okay, example problem number one. We're looking for the derivative of f. Okay, in this case, f is this function times this function. Okay, so right away, a light bulb should be going off in your head. Oh, I have two functions multiplied by each other. That means I'm going to need product rule. Okay, so first thing I'm going to do with product rule to solve this is I'm going to set up my f and f prime and my g and my g prime. Okay, because if you remember, the formula is just f prime g plus g prime f. So we need to find all of these and then just basically lump them together. It is also important to note that I am saying that this is my f and this is my g, but these f's are not the same. I'm just using it with the formula. So it's a formula f versus the original function, just giving it, it's defined as f. So just know that my f is that first one, and I'm going to fill that in. This is e to the x, and this is sine x. Okay, the derivatives is the next thing I'm going to find here. So the derivative of e to the x is itself e to the x. The derivative of sine x is cosine x. So I'm going to put that in there. Okay, and then from here, I'm just going to use this formula right here. So it's f prime g, so it's f prime g plus g prime f. And that's basically the answer. Now, if you notice the multiple choice, it actually factors out the e to the x on that, so you might want to write it that way if you want, or you can just select the answer. I guess this is kind of redundant, but you can see that the answer for this one is C, because that is the answer that we got using product rule. All right, let's do another example. All right, this one is a little bit more conceptual than the one we just did, because now it's saying, you know, there's specific values that are given. There's some function g, which is x squared times f, so we have two functions multiplied, and we're looking for g prime of 3. Okay, so first thing that we need to do is find g prime. So whenever you see this, it says g prime of 3, find g prime first, and then once you're done finding g prime, just plug in 3. Okay, so that's what we're going to do. G prime is going to be, we're going to use product rule on this. So we have f and f prime, g and g prime. Again, you don't have to do it this way. This is just kind of how I like to do it. So we have x squared there. In this case, our g is actually just f in this case, which is getting a little confusing because we have these f's and these g's all over the place. But just know that this f is not equal, this f right here is not equal to this f here. So to kind of change that up, I'm just going to say this is f1, just so it's kind of different. And I'll put a little 1 here, here, and here, so we can kind of tell the f from the f1, f sub 1. All right, f prime is 2x, and then g prime is f1, f sub 1, the derivative. So f sub 1, and we're going to do the derivative of that. Okay, so then let's write this in now. So we have f prime g, so it's 2x times f of 1, f sub 1, I'm sorry, plus g prime, which is f sub 1's derivative, times x squared. Okay, next thing we need to do is just plug in 3. So we have our derivative. Now we just need to plug in 3 for all the x's. So that's going to be 6 times f sub 1 of 3. So there's going to be a x in there, and it's going to be 3, plus f sub 1 derivatives at 3 times 3 squared, which is 9. Okay, what's great about this problem is this value and this value are given right here. So now I'm just going to put those values in. So it's going to be 6 times 4 plus 5 times 9. 24 plus 45 is going to be 69. Everyone's going to get a good chuckle about this, but that is the answer for that one. G prime of 3. Okay, not as straightforward as the other one, because we have this f sub 1 function that we have in there, and it's getting a little confusing. Things are getting a little, crazy with the formula, but if you follow the formula, you should be able to get that answer. And let's look at this last example right here. Okay, this one's another tricky one. It looks like there's a quotient in there, so we're going to have to use quotient rule. But there's also this table. This is kind of crazy. All right, first of all, it defines h right here, and it says let's h prime of 2. So this is basically the instructions. Step 1, find the derivative. Step 2, plug in 2 for x. That's all we have to do. So let's do it. H prime is equal to the derivative of h, which is this thing right here. We have to do that derivative. Okay. To do that derivative, we're going to have to use quotient rule because it's a quotient. So let's see here. We have our f and f prime, and we have our g and our g prime. Okay, f is whatever's on top, which in this case it's 4f, which is going to be confusing on this. So I'm going to just put f1 again, just to make it a little bit easier, because the formula, let's write that in green so you can actually see it. So that's f sub 1. This is going to be our g sub 1, just so it's a little bit easier to work with. All All right, the derivative of f, which is 4 times f sub 1, is just going to be 4 times the derivative of f sub 1. Okay, g is going to be just g sub 1 plus 1, because it's that thing on the bottom right here. And then the derivative of this is going to be g sub 1's derivative plus 1's derivative. 1's derivative is just 0, so we don't need to worry about that. All right, so now let's follow the formula. It's going to be gf prime, so girlfriend prime, so g times f prime, which is 4f sub 1 prime, minus, okay, now it's going to be g prime f, so that's going to be g sub 1 prime times 4 times f sub 1. Okay, and then we're going to subtract all this by g squared, which is just going to be g sub 1 of x plus 1 quantity squared. Holy cow. This is looking messy, but we can figure it out. Okay, once we found the derivative, check. Okay, next step is plug in 2. So that's what we're going to do. H prime of 2 is equal to g sub 1 of 2 plus 1 times 4 of f sub 1's derivative of 2 minus g sub 1 of prime of 2 times 4 f sub 1 of 2. So I just basically plugged in 2. So I basically just plugged in 2 for all those functions that are in this purple step there. Once I do this, I will. Okay, now all of these values are all found in this table up here. I'm going to add little subscripts of 1 on all these so we know that it's related to that pink step right there. And we're just going to plug in values. G sub 1 of 2, okay, well that's -3. So that first value is -3. Put -3 in there, plus 1. Okay, 4 times f prime, f sub 1 prime of 2 is 1/2, so that's just going to be 2. So times 2. Minus, this value right here is right here is 2. Times 4. Let's move this over a little bit. 4 times f sub 1 of 2, which is -3, so that's going to be -12. Write that a little neater, and then we're dividing all of this by g sub 1 of 2, which is -3 plus 1. It's -2 squared is 4 on the bottom. So now we got to do some arithmetic, so it's -2 times 2. So now we're going to do some arithmetic, so that first one's -2 times 2 is -4 plus 24, because that negative, and then it's all divided by 4. All right, and then from here it's 20 divided by 4 is 5, so the answer for this one should be 5. But holy cow, so many steps on this one. So this one's not as straightforward as the other ones because there's a table, okay? This other one that we did just before it wasn't as straightforward either because there were certain values of the function given, and g of x was x squared times some function that we don't actually know about, we just know its values. Comparing that to problem number 1, which is pretty straightforward because the function is just e to the x sine x, and we just used product rule. Make sure you are aware of how to do every single one of these types of problems, the conceptual and the more procedural. When it comes down to it though, it's just using these formulas of product rule and quotient rule. And if you have any questions on this section, definitely let me know. And let's go on to that last section, which is chain rule. All right, this last subsection of 2.2 is going to be all about chain rule. I actually kind of call this rule something different sometimes. I call it onion rule because really with this rule, it's when you're doing the derivative of layered functions. So if you have a function that's layered, it's a composite function, it's a function inside of another function, then you're going to want to use this rule. Now, what does the rule look like? It looks like the following. Okay, so if you notice g of x right here, I'm going to highlight this in red, is inside of the f of x function, and we're doing the derivative of this. And if you notice, the g of x stays inside here, but you have to put it inside f's derivative. So it's like you have to find the derivative of that f of x function and then basically put g of x in there, and then you're eventually multiplying it by the derivative of g. Okay, if you use this more as onion rule, the rule that I was just kind of talking about, that's what I like to name it. Just like peeling back an onion, you would start with the outer layer first, you do that derivative, and then you work your way in. But they call it chain rule for whatever reason. But either way, we're going to do some examples, and hopefully it makes more sense. Chain rule also allows us to find the derivative of inverse functions. Inverse functions, if you remember, it's whenever there is a function in which you did f of g of x, it's equal to x. Essentially what happens is the f and the g cancel, and you end up with x, okay? Inverse functions like multiply and divide, those are inverses. Adding and subtracting, those are inverses of each other. Basically, they cancel each other out, okay? Base e and ln, those cancel each other out, okay? So that's the definition of an inverse. F and g are inverses if the following is true, okay? And when that happens, one way that you've probably been taught in the past is just flip out the, switch the x and the y. As you can see, that's kind of what they did here. We have q and we have p. Q is up and down, P is left and right for this one, and then it flip-flops here because it's the inverse. If you notice right here, it's got this f to the -1 power right here, where this one just has an f here. It is important to understand that this is not equal to 1 over f. It looks like it would be because of the -1 power. It's just really poor notation on math's part, where it looks like it's a -1 exponent, but it's not. It just means inverse, and so it's not equal to 1 over f. Really want to stress that. This is not equal. Make sure you understand that. It's the inverse of it. And again, the inverse is what this states right here. Okay? But we need to figure out the derivative of the inverse. Okay, well, here's the formula right here. If you have an inverse function, so f of g of x is equal to x, well, the derivative, which is in this case g, it doesn't matter if it's f or g, f and g are inverses of each other. If you have this right here, g prime of x is equal to this formula at the bottom. Now you might be wondering, where did this come from? Well, it actually came from chain rule. And to kind of show you that, I am going to delete this and just basically, actually what I'm going to do is I'm going to shrink this down and kind of just put it off to the side here. But I'm going to show you where this comes from using chain rule. It's kind of a good practice to use chain rule. So what we're going to do here is we're going to do the derivative of both sides here. So the derivative of this side, and then we're going to do the derivative of this side here. Okay, the derivative of this layered function right here is what we just talked about in the previous slide. It's just chain rule. I'm sorry, the second, two slides ago. The derivative of f of g of x right there. Okay, so that's just chain rule. And essentially what we're going to do is I'm going to show you that onion rule thing I was talking about. We're going to do the derivative of the outside layer. This is the outside layer because it's g of x is inside of f. So the outside layer derivative first. So I'm going to do that derivative. Everything else stays the same for the inside layer. Next, I'm going to multiply it by the derivative of the next inside layer, which is this g of x. So the derivative of g of x. Okay, so the left side of that equation is completely done with this derivative right here. Okay, the derivative of x on this side is just 1. Now we want to figure out the derivative of the inverse. Well, f and g are inverses of each other, and g prime is right here. So what I'm going to do is just solve for g prime by dividing this out right here on both sides. So you divide that on both sides, you end up with 1 over f prime of g of x right here in blue. And if you notice, it matches the derivative of the inverse right here. Okay, you do not need to know where that comes from, but I like to show it because sometimes students forget the derivative of the inverse because it's a weird rule there. G prime is equal to 1 over f prime of g of x. It's hard to memorize that sometimes. So when in doubt, you can always just solve it out really quick. But you have to remember the derivative, you have to remember the inverse function is when you have f of g of x is equal to x because the f and the g cancel out. Okay, when you have a composite function and they cancel out and it's equal to x, that's an inverse. If you do the derivative of that, you get this blue highlighted part that I'm highlighting right now, which is the same thing as this up here. Okay, that's just where it came from. All right, let's use this in action and see, hopefully this makes more sense as we go. All right, this one is just straight up derivative. It's just chain rule. There's no inverses in this problem, so it's going to be a little bit easier than the thing I was just talking about. But we will do some inverse problems as well. All right, this one, hopefully you see that it's got a function right here, and it's inside of this function right here. Okay, it's not being multiplied. It's not being the quotient of it. It's not being added. It's not any of the other rules. It's literally just a function inside of the 4th power function. So what we're going to do here is we're going to use onion rule, chain rule. We're going to do the derivative of the outside layer. That's a power, so I'm going to bring that power down. So I'm putting the 4 in front, essentially, for the derivative. And it's 4 times e to the 3x plus sine of 2x. And then power rule, we get the -1 from the power, so we have a 3. Okay, that layer is done. That 4th layer is done. So now we're going to do the derivative of the inside layer. So it's onion rule. We're just breaking it down layer by layer. We got the 4th power layer done. Now we just have to multiply by the derivative of what I underlined in orange there. The derivative of e, so it's multiplied by the whole thing. The derivative of e to the 3x is e to the 3x, but there's an inner function right here. So the outside layer is the e, that's e to the 3x, but then you have to multiply by the inner function of the derivative of 3x. The derivative of 3x is 3. Okay, so it's like a chain rule inside of a chain rule on this one. Okay, plus the derivative of sine, which is cosine, 2x, but there's an inner function on this one too, of 2x, so you have to multiply by that derivative, which is just a times 2. Okay, I kind of ran out of room here, so I'm going to rewrite this really quick. So your answer is going to be something like 4 times the quantity e to the 3x plus sine of 2x to the third power times 3e to the 3x plus 2 cosine of 2x. And this all has to be in parentheses, otherwise it won't distribute right. So that's a mess, but luckily it actually matches one of the answers here, which it looks like it's going to be D. Okay. It's also important to note that you cannot distribute this 4 here because this is not 4, this is not e to the 3x plus sine 2x, it's actually cubed. So you can't just distribute this here because there's only one 4. There's not 3 of them. If there's 3 of them, you could. But you cannot distribute that there, so that's why they didn't do that. But anyway, yeah, you might have to watch this one a couple times because it definitely has a lot of steps and a lot to look at. I tried to color code every single layer there with the answer key, so hopefully that helps. But if not, definitely make sure you reach out and get some help on it. Okay, the next one, example problem number 2. Okay, let f of x be defined as e to the hx. Okay, so right now you should see that h of x is buried inside of that base e function. So it's inside of it. It's not adding, subtracting, multiplying, dividing. It's just the exponents inside of that base e function. H is differentiable, so that means the derivative exists everywhere, which is great. Which of the following is equivalent to the derivative of f with respect to x? Okay, so we need to figure out what is f prime of x. That is essentially what we're looking for. Okay, we're going to need chain rule on this. So the derivative of f is equal to the derivative of e to the h of x power. So it's a layered function, so we're going to do the derivative of the outside layer, which is this one first, because then this h of x is inside of that base e. So the derivative of base e is just itself, so I wrote e to the h of x, and then I have to multiply by the derivative of the next layer, which is h prime of x. So this is the derivative right here. Okay, there's nothing else we can break down because we don't know what h is. So which one of those matches this? It's going to be c right here. Okay. Next, we have an inverse problem. This is going to be the last problem for this section. It says let f be defined by this whole thing right here, and let g be the inverse of f. So that just means g is the inverse of f. It does not mean f to the negative 1 power. Make sure you understand that. It's not f to the negative 1 power, where g of 3 is equal to 1. What is the value of g prime of 3? Okay, first thing I'm going to start with is we need to find the derivative of g. Okay, you can shoot right to memorizing that formula if you want, or you can write, f of g of x is equal to x. Do the derivative of both sides, which is just going to be f prime of g of x times g prime of x is equal to 1. Okay, we're solving for g prime. Okay, so we're basically doing the same steps that we did last time. So now we have our formula for g prime of x. Okay, again, you could have just memorized that as well. It doesn't really matter. Okay, now from here, we want to find g prime of 3. So everywhere there's an x, I'm going to replace it with a 3. So now this is going to be equal to 1 over f prime of g of 3. Okay, well, what's g of 3? We don't know. Well, actually, it says it right here what g of 3 is. So really, so we're finding this part right here. Really, this is just 1 over f prime of 1, because g of 3 is 1. Okay, but we need to figure out what's f prime of 1. Well, first thing you need to do is find what f prime of x is, and then just plug in a 1. Well, f prime of x is 3x squared plus 2x plus 1. How did I find that? Well, I found that by just doing the derivative of f. That's what it says to do. So now we're going to plug in 1 for x to solve this. So now it's going to be 3 plus 2 plus 1 is 6. So that means this value right here is equal to 6. Okay, don't forget the 1 over though. So this is going to be 1 over 6 for the answer for that one. Okay. Chain rule is by far probably the second hardest thing in this unit. I would say the hardest thing in the unit is implicit differentiation. So definitely make sure you focus and ask questions if you got them on this, because this is confusing. This is definitely hard to teach yourself. So definitely reach out if you are having struggles. The next section of this video is going to involve implicit differentiation in section 2.3. So that's what we're going to go over next. All right. This is going to be the last section in Unit 2, Implicit Differentiation. I would say that this is definitely the most complicated part of this unit, so definitely make sure you pay close attention, take really good notes, rewatch, rewind, slow motion, fast forward, whatever you need to do for this video. Ask me questions in real life. That would be great too. Whatever you need to be able to understand this, definitely make sure you reach out, because this one is complicated, but with enough help, you should be able to get it. So implicit differentiation. Okay, before we start with implicit differentiation, we need to figure out what's an implicit function, or what's an implicit equation. What does that even mean? Well, here's a little graphic that kind of shows you the difference between an explicit function and an implicit. Explicit is what you are used to. Okay, y equals something, a function that can be expressed as an equation in terms of one variable. So in essence, you're solving for y. You can solve for y, you can get y on one side and x is on all the other. That's an explicit equation. Okay, an implicit equation, on the other hand, you cannot do that. Okay, the function is implied by an equation. You can't separate the variables. Okay, it's difficult to express y in terms of x for this particular one. You can't just say, you can't have it as y equals. Okay, with explicit, we just follow the old rules that we had before. All the derivatives we've done so far in this unit were all explicit functions, so we were able to do the derivatives no problem. Implicit, there's a little bit of math trickery, I guess, if you want to think of it that way, that we have to do in order to find this derivative. So just definitely make sure you pay attention on this so it makes sense. Here is the formal definition of implicit differentiation. It says d of x, d over dx, which means the derivative. So we're doing the derivative of some function, but the function is expressed in terms of y. Okay, we are used to f being equal to y. Okay, but now it's saying f of y. So the function is defined with y's. Well, what do? Well, based on this formula, you take the derivative like normal, but then you have to also tack on this multiplication of dy over dx. Okay, this is called the implicit, well, it's not called this, but I would call it the implicit differentiation rule. Whenever you take the derivative, if it doesn't match with whatever variables it is, so for example, this one's x and this one's y, you do the derivative like normal. That's what this is essentially. It's the derivative of this, like normal, but then you have to tack on that multiplying by dy over dx. Okay. Now to prove this, I'm going to show you a little bit of, this is a very informal way of showing this, but I definitely think it's a good way of showing this, so definitely pay attention to this. Oops, I did not want to do that. Just going to move this up really quick so I have some room. I'm going to shrink it down a little bit. Put it right here. Okay, to kind of prove this, I'm going to show it in the following way. So we're going to do the derivative of, let's just say, x squared, because we're used to that. Power rule, this ends up being 2x. You should be able to do that in your sleep. Okay, but what happens if I want to do the derivative with respect to with respect to x of y squared? Okay, this y obviously does not match this x. Okay, that's a problem, because the limit definition of derivatives, everything's in terms of x on that. So how can we solve this out? So what we're going to do is the following. This is like the equivalent of spreading your vegetables out on your plate. I don't know if you ever did that as a kid. I know I did. I had vegetables on my plate. What I did is I spread them out so my parents wouldn't realize that, oh, there's not less veggies. It just looks like there's less veggies. So they didn't understand that, they probably did. They were just being nice to me or whatever. But it's essentially, you're spreading out the vegetables. Everything is still equal. You have the same amount of vegetables, but you're able to get something else out of it, like not eating them because your parents think you ate more. That's essentially what I'm going to do in this case. So what I'm going to do is I'm going to change that dx to dy. So we're going to do the derivative with respect to y of y squared. That is perfectly legal to do. The only problem with this is you would also need to make a dy and a dx over here, because if you multiply this across, you would still get where you started. Okay, I'm going to back up and kind of reset on this. Okay, first thing I'm going to do is rewrite this. So it says dy squared over dx. Okay, it's just one fraction. I basically just threw this on top. Perfectly legal to do that. saying the same thing, the derivative of y squared. From here as a fraction, though, I'm going to separate this out. So I'm spreading the vegetables on the plate here. Okay, and by doing this, you'll notice that I can put a 1 here and a 1 here, and it's still completely equal, if you multiply across, it's still completely equal to the green step, to this step right here. Nothing's changed. But in order to do that derivative of the y, you have to do dy on the bottom here. But if this is dy, this also has to be dy. Okay, so far this is still completely equal, but now we can actually do something with it because the y matches what you're doing with the derivative with respect to. Okay, this part right here is just going to be equal to 2y, just like the derivative right here of x squared with respect to x is 2x. Well, that part's 2y. But now we have this dy over dx that we have to tack on to the end. That ends up proving why we need that dy over dx at the end. So you do the derivative like normal, and then you just tack on a times dy over dx. And ultimately, that's what we're going to be solving for, is dy over dx, because if you remember from earlier in this video, dy over dx means derivative. Okay, so that's essentially the implicit differentiation rule. If you don't understand the spreading the vegetables explanation that I had on the bottom, you don't actually need that. But what you do need is the implicit differentiation rule, where you're doing the derivative with respect to y. So make sure you do the derivative first, and then just tack on a dy over dx at the end, and you're good to go. Let's do some example problems so this makes more sense. Okay, example problem number 1. So y is equal to ln of 3x plus 4y. If you notice there's y in 2 different spots, we cannot solve for y. We cannot get y by itself, so we have to use implicit differentiation to figure out the derivative. That's what it's asking for. What is the derivative on this? So first thing I'm going to do, and this is always step 1 when you're doing these problems, is take the derivative of both sides with respect to x. So d over dx on both sides. So that's what I'm going to do. D over dx, d over dx. Okay. The derivative of y is just going to be, because the x and the y don't match, so you do the derivative like normal, which is just the derivative of y is 1, times dy over dx. If you remember, the y does not match the x, so you just have to tack on that dy over dx. This one's also kind of easy because you can just put the y on top and it's dy over dx. You can ignore the times 1, but again, we're just using that implicit differentiation rule. The y and the x don't match, so do the derivative like normal, that's this, and then tack on a dy over dx at the end because it doesn't match. Again, if you don't know why, you can go back to the spreading the vegetables explanation, or you can just know that's the rule, you have to follow the rule. This other one is chain rule, because we have a function inside of this ln function. So we're going to do the derivative of the outside layer first, which is the ln. So it's going to be 1 over 3x plus 4y. So that's the derivative of this layer, ln. But now we have to multiply by the derivative of this layer. The derivative of 3x is 3. The derivative of 4y is 4, but the y doesn't match the x. So you have to multiply it by dy over dx. You have to tack that on at the end. Have to. So now if you notice, we have a dy over dx on the left, right here in green, and then we have one right here in purple. We need to just bring those together, essentially, and then once we do that, we can solve for dy over dx. So the first thing I'm going to do is multiply both sides by that 3x plus 4y. So this is going to be 3x plus 4y times dy over dx. On the right side, it's going to cancel, so you're just going to be left with 3 plus 4 dy over dx. Okay, we're just solving for dy over dx, so we need to get it on both sides. Let's distribute first. Actually, let's subtract 4 dx on both sides first, because it's going to make things a little bit easier. So we have, well, I'm just going to distribute. What the heck? So 3x times dy over dx plus 4y times dy over dx minus 4 dy over dx, because again, I subtracted this on both sides, is equal to 3. All right, from here, I'm going to factor out a dy over dx, and you're going to be left with 3x plus 4y minus 4 is equal to 3. Divide both sides by 3x plus 4y minus 4, so we're going to divide both sides by this whole mess right here, and you're going to get 3 over 3x plus 4y minus 4, which is this answer right here. I'm not even going to write it out because you can just see it's 3 divided by that big mess right here. So it's 3 divided by the mess, which is D for the answer. Holy cow, that was a lot of steps. Okay, you might want to rewatch that one, or again, ask questions if you got them. Here we go. Example problem number 2. Holy cow, this is a lot of parts. For part A, it says consider the curve xy squared minus 2x cubed equals 2 for y is greater than or equal to 0. Show that the derivative is equal to this. All right, so for part A, all we need to do is show that the derivative is equal to that. It basically gives us the answer already. We just need to do the derivative of A and make sure it matches. So it gives us the answer, we're just proving it. So part A. So for part A, first thing I'm going to do is copy and paste this. So I'll have to rewrite it. Put that right here. Blow it up a little bit. There we go. Okay, first step whenever you're doing implicit differentiation is the derivative of both sides with respect to x. So that's what I'm going to do. Derivative here, and then the derivative here. I'm trying to put that in front. There's not a lot of room. Okay, derivative of this thing right here. Okay, holy cow. You have to notice that it's actually product rule on this because it's x times y squared. So you need to do f prime, which is 1, times g plus g prime. G prime is going to be 2y dy over dx. So we're doing the derivative of y squared times f minus 6x squared. So I'm doing the derivative here is equal to the derivative of 2, which is 0. And this one's a little bit easier than the last one we did because the dy over dx is just in one spot. So we just need to solve this right here. I'm going to put everything else on the other side. So I'm going to add 6x squared on both sides. I'm going to minus y squared on both sides. And you're going to get 2xy dy over dx, I just put this x in front over here, is equal to 6x squared minus y squared. Divide both sides by 2xy, and you get 6x squared minus y squared, divided by 2xy, which it says that's what you're supposed to do for this problem, is show that it's equal to that, which I just did. So we're good to go with that answer for A. Now B is further down the rabbit hole a little bit. Write an equation of the line tangent to the curve at 1, 2. So we need an equation of a tangent line at 1, 2. Okay, so that means we need a y equals mx plus b, or just any equation of a line, to basically figure out what that equation of the line is based on that derivative right there. Okay, so first thing I'm going to do is find my slope. So to find my slope of this equation of the line, I'm going to use my slope equation, which is just the derivative. So it's going to be 6 times 1 squared is 6, minus y squared is 4, because we're using this is my x and this is my y, divided by 2xy, which is just 4. So the slope for this ends up being 1/2. Okay, I'm going to do this in point slope form because it's going to be a little bit easier. We can just do y minus 2 is equal to 1/2 times x minus 1. And there we go. That is the equation of the tangent line for this problem. Okay, write an equation for the line tangent. We did that. Sweet. All right. C. Find the x-coordinate, P, in which the line tangent to the curve at P is horizontal. So if it's horizontal, that means that the slope is equal to 0. If you think about a horizontal line, like this horizontal line right there, the slope at any point there is equal to 0. So if we want a horizontal tangent line, all we have to do is set our derivative equal to 0. So that's what I'm going to do. Derivative is equal to 0. Well, the only time the derivative is equal to 0 is when the numerator is equal to 0. And you have to make sure you don't have a 0 on the bottom because you'd have 0 over 0. That's not 0. But in this case, we don't really need to worry about that. So we just need to solve this right here. I'm going to add y squared to both sides, and you end up getting 6x squared is equal to y squared. But that doesn't help us figure out exactly what the coordinates are, because that's what it's asking for. What's the x-coordinate in which the line tangent is horizontal? So what we need to do is actually use the original equation to figure out what's going on, what's the x-coordinate for this. So what I'm going to do here first is solve for x. So y squared over 6, and then we're doing the square root of it. So I divided both sides by 6. I did the square root of it. Make sure you do plus or minus on that. And now we need to solve it. We're going to solve it based on the original, and I'm going to use that equation on the right to basically figure out what this x value is. Let's see here. So y squared. So what I'm going to do on this right here is solve for y squared. So it looks like it's going to be 2 plus 2x cubed divided by x is equal to y squared. So I'm going to throw that in for the x and basically just solve for x on this. So we have 2 plus 2x cubed over 6x, we're doing the square root of all that, is equal to x. Okay, forget the plus or minus for now because we're going to be squaring both sides. And you end up with 2 plus 2x cubed over 6x is equal to x squared. Okay, I'm going to multiply both sides by 6x, and you end up with 2 plus 2x cubed is equal to 6x cubed. Holy cow, this is getting crazy. I love it. All right, and then we're going to have 4x cubed here is equal to 2. Divide both sides by 4, cube root it, and x is equal to the cube root of 1/2. Holy cow. Okay, so that's the answer for this one, where the derivative is equal to 0. It just involved a lot of algebra, more algebra probably than calculus on that one to get that x coordinate. And last but not least, we have part D, which it's so far up there, I don't even know what it's asking for. Let's see here. Find the second derivative at 1, 2. So that's that weird notation that we talked about before for second derivative. Okay, the second derivative at 1, 2. Okay, first thing we need to do is find the derivative of the derivative that we already had, which in this case is that 6x squared minus y squared over 2xy. So we're going to do the derivative, whoops, let's do a different color. So we're going to do the derivative of 6x squared minus y squared over 2xy. Okay, hopefully you see that this is quotient rule because you have a function divided by another function. So this is going to be equal to g times f prime minus f times g prime, which, holy cow, that's going to be product rule. So f prime g plus g prime f, and then we're dividing all this, and then we're dividing this all by 2xy quantity squared because you're dividing it by g squared. Holy cow, this seems like a lot. But it actually isn't, because we're looking for where it's 1, 2. So all we really need to do is plug in 1, 2 for all of these. Okay, so that's a 1, that's a 1. The derivative here is actually equal to 1/2 because we figured that out in part B. Okay, that's a 1, that's a 1, that's a 1. Okay, so all the y's now are 2's. So this one you're going to get a 4 times 12 minus 4 times 1/2 is 2, minus 6 minus 4 times 2 times 2 plus 1/2. So that's 5/2. And we're dividing this all by 2 times y is 2 times 2 is 4, divided by 4 squared is 16. So we're dividing by that 16 there. This is 10. This is 2. This cancels. So now you end up with 40 minus 10. This cancels here. 40 minus 10 is 30. So it's 30 over 16, which simplifies to 15 over 8. Holy cow, that was a lot of steps. That was definitely a rough problem. Hopefully you're seeing that implicit differentiation is among one of the harder things in this section so far, but you should get 15 over 8 for that one. Holy cow, you're going to have to probably rewatch that one a couple times. All right, on to the last one. I love it, but man, that's crazy. All right. Find the value of the derivative at 0, 1. So first thing we need to do is find the derivative of this whole thing here, and then just plug in 0 and 1 for the x and the y, and we should be able to find that. So first step is do the derivative of the left side. So it's going to be e to the y times dy over dx minus e to the y squared times 2y times dy over dx. Okay, because the inner function of y squared, you have to multiply it by its derivative, which is 2y, is equal to 1 minus 3x squared. So I did the derivative of the left, the derivative of the right with respect to x. Now I need to solve for this value right here, but it's in 2 different spots. Before I do that though, I'm going to plug in 0, 1 for my x and my y because it's going to make it a little bit easier on me if I just do that right away. So the y is 1, so I'm going to get rid of all these y's here. The x is 0, so this whole thing is gone. So now we can just solve this out. So it's going to be e dy over dx minus 2e dy over dx is equal to 1. Okay, well, e minus 2e, so I'm going to factor this out, is equal to negative e is equal to 1. Solve for dy over dx, and you get negative 1 over e, because I divided both sides by negative e there. So the answer for this one should be A. All right, so holy cow, implicit differentiation is definitely rough. Make sure you practice this a lot. The main thing is that you just do the derivative like normal and then tack on that dy over dx at the end because it does not match with the x. The rest of it's just all the other rules that we've already covered in the section. Definitely the hardest section of the whole unit. If you have any questions about anything in this unit, anything in this video, whatever, definitely make sure you reach out, and I will see you next time.